A crank turns at a steady pace. Its pin travels around a circle, while a cyan carriage slides left and right beneath it. A recording pen follows the carriage and leaves a smooth, repeating trace. The machine can show where the carriage has been. Can it tell us where the carriage will be 2 seconds from now? The vertical marks tell us position, but the horizontal direction has no scale. A beautiful curve without an input is not yet a useful function. We need a number that records how far the crank has turned, and then a rule that connects that number to the laboratory clock. Last time, one rotating point gave cosine horizontally and sine vertically. We use that result now. If this is unfamiliar, watch episode 4 first. Degrees can label a turn, but the circle already contains a more physical ruler. The only length built into every circle is its radius. So instead of dividing a turn into an arbitrary number of pieces, let the radius itself measure the rim. Keep every point of this ribbon visible as it bends onto the circle. Its starting end stays on the positive horizontal ray. Its far end slides along the rim until one full radius of arc has been covered. Now the arc length, S, equals the radius, R. Look from the center to the two ends of that arc. The angle between those rays is 1 radian. 1 radian is therefore not 1 degree. It is the angle that cuts off 1 radius of arc. If the arc covers 2 radius lengths, the angle is 2 radians. If it covers half a radius length, the angle is half a radian. In general, the radian measure theta equals arc length S divided by radius R. Arc length and radius must use the same length unit. Their units cancel in the ratio. Theta is therefore a pure number, but we keep the word radian to say that this number measures angle. Keep theta equals S over R on screen. Multiply both sides by R, one operation. The R factors cancel on the right, leaving R theta equals S. Write the same result in physical reading order. S equals R theta. To measure one complete turn, we need only the familiar circumference fact. Pi is circumference divided by diameter, and diameter is 2 radii. So the circumference is 2 pi r. We will use that fact here, not rederive pi. For a full turn, S is the entire circumference, 2 pi r. Substitute that arc into theta equals S over r. The radius cancels, leaving 2 pi radians for one complete turn. A quarter turn is pi over 2. Half a turn is pi radians. 3/4 is 3 pi over 2. One full turn is 2 pi. These are not a new table to memorize. Each mark is a fraction of the measured circumference. We also need direction. By convention, counterclockwise turns are positive and clockwise turns are negative. The same quarter turn upward is plus pi over 2. The quarter turn downward is minus pi over 2. Now set the radius to 1 unit. In S equals R theta, multiplying by 1 leaves S equal to theta. On a unit circle, the number of radians equals the numerical arc length measured in radius units. Angle and arc length are related, but they are still different physical quantities. This is why radians fit physics. Hold the wheel center fixed and rotate it through theta radians. A marked rim point sweeps the circular arc distance S equals R theta. No degree conversion factor is needed. The angle measure speaks directly to a physical distance. Bring the recorder back. Its blank horizontal axis can now inherit the circle ruler. 0 marks the starting ray. Pi over 2 marks a quarter turn, pi a half turn, 3 pi over 2 3/4, and 2 pi 1 complete turn. The horizontal graph coordinate is now the input angle theta, measured in radians. The vertical coordinate is a projection reading. For the cyan strip, it is cosine theta. For the mint strip, it is sine theta. The graph does not draw the circular path, it records one measured coordinate against angle. Start at theta equals 0. The point sits at the rightmost edge. The horizontal projection is 1, so the cosine pen begins at 1. The vertical projection is 0, so the sine pen begins on the center line. Turn steadily to pi over 2. From the same changing angle, the horizontal projection shrinks while the vertical projection grows. At the quarter turn, the horizontal value reaches 0 as the vertical value reaches 1. The cyan trace falls as the mint trace rises, and both pens remain attached. Pause and read both values. Continue to pi. The point reaches the left edge. Cosine reaches -1, while sine returns to 0. The signs are not separate rules. The graph simply records where each signed projection lands. At 3 pi over 2, the horizontal projection is 0 again, and the vertical projection is -1. The cyan curve crosses its centerline, while the mint curve reaches its lowest point. At 2 pi, the point returns to its starting place. Cosine returns to 1, and sine returns to 0. One circular turn has written one complete cycle of each graph. Let the crank continue through another turn. Nothing resets. The same sequence of projection values repeats from 2 pi to 4 pi. Sine and cosine accept angles beyond one turn because their input records accumulated rotation. The smallest positive angle shift that reproduces the entire pattern is 2 pi. In the angle domain, sine and cosine have period 2 pi radians. Adding 2 pi changes the accumulated turn, but not the point on the circle or either projection. The graph also extends left of 0. A negative input means turning clockwise from the reference ray. The same projection mechanism writes the negative angle side of each curve. The graph is a function defined across a continuous angle line, not a single lap around a dial. Now align the two finished traces. The sine curve has the same shape as the cosine curve, shifted right by pi over 2 in the angle input. Point by point, sine theta equals cosine of theta minus pi over 2. The quarter turn separation comes from the two perpendicular projections. The angle ruler controls horizontal progress through a cycle. What controls the vertical size of the motion? Return to the physical crank and increase its radius while keeping the same angle. Every horizontal projection is multiplied by the new radius. The carriage now reaches farther on both sides of equilibrium. In the position graph, that maximum distance from the centerline is the amplitude, A. Amplitude is measured from equilibrium to one extreme. The full distance from the negative extreme to the positive extreme is 2a, nada. Keeping that distinction prevents a common factor of 2 mistake. For a crank of radius a, the horizontal position is a cosine theta and the vertical position is a sine theta. Changing a stretches both graphs vertically. It does not change the radian input or the 2 pi angular period. The graph can now predict position from angle, but the laboratory clock does not report radians, it reports seconds. To answer the opening question, we must find the crank angle at each time. Suppose the motor turns uniformly. Equal time intervals then produce equal angle intervals. Angular frequency, omega, tells how many radians the angle advances each second. If the crank starts at theta equals 0 when time is 0, then after t seconds its angle is omega times t. The relation is theta of t equals omega t. Omega carries units of radians per second. For example, omega equals pi radians per second means the crank advances half a turn each second. It completes a full 2 pi turn in 2 seconds. Keep the known projection function x of theta equals a cosine theta on screen. Substitute theta equals omega t only into its input. One replacement gives x of t equals a cosine of omega t. Now the same curve can answer a clock question. Its plotted outputs do not move. The horizontal labels transform from accumulated radians through theta equals omega t into elapsed seconds. The recorder is now a position versus time graph. Call the time for one complete cycle t, the period. During that time, the angle advances by 2 pi radians, so omega times t equals 2 pi. Divide both sides by omega. The period is t equals 2 pi over omega. A larger angular frequency produces a shorter period because the crank completes its 2 pi journey sooner. Ordinary frequency, f, counts complete cycles per second. It is the reciprocal of period, f equals 1 over t. Its unit is hertz, meaning 1 cycle per second. Each cycle contains 2 pi radians. Therefore, radians per second equal 2 pi times cycles per second. Angular frequency and ordinary frequency are related by omega equals 2 pi f. They describe the same pace with different units. So far, the crank began on the positive horizontal ray when the clock reads 0. A real experiment may start recording after the crank has already turned. Call that initial angle phi the phase angle. Positive phi moves the starting radius counterclockwise. Negative phi moves it clockwise. The sine belongs to the same directed angle convention used for theta. Phase changes where the cycle begins, not how quickly it advances. After time begins, the crank adds the uniform advance omega t to its starting angle phi. The general angle is theta of t equals omega t plus phi. At time 0, omega t vanishes, leaving theta of 0 equal to phi. The horizontal projection was a cosine theta. Replace theta with omega t plus phi, one substitution and nothing more. The result is x of t equals a cosine of omega t plus phi. Read the model from the physical controls. A is maximum displacement from equilibrium. Omega is angular frequency in radians per second. Phi is the starting angle in radians. Each parameter changes one visible property while the others can remain fixed. Use a projection slider with amplitude 0.20 meters. Let its frequency be 0.5 Hz, one cycle every 2 seconds, and let phi be 0. Then omega equals 2 pi f, which is pi radians per second. Substitute those values. Position is 0.20 cosine of pi t meters. Before moving the mechanism, predict the checkpoints. At time 0, cosine 0 is 1, so x is positive 0.20 meters. Now predict time 0.5 seconds. The angle is pi times 0.5 or pi over 2. Cosine of pi over 2 is 0, so x is 0 meters. At 1 second, the angle is pi. Cosine of pi is negative 1. Multiply by 0.20 meters, and x is negative 0.20 meters. At 1.5 seconds, the angle is 3 pi over 2. Cosine there is 0, so x is 0 meters again. At 2 seconds, the angle is 2 pi, and cosine returns to 1. The slider should return to positive 0.20 meters. One complete prediction period is now closed. Now release the crank. The carriage reaches every predicted point at the predicted time. The curve is no longer a remembered shape. It is a schedule for physical position. Place an ideal spring and mass beside the projection slider, but do not connect them. In introductory mechanics, an ideal spring can produce a position with the same cosine form. The two traces can match even though the physical causes are different. Uniform circular projection is an exact geometric model of sinusoidal position. Ideal simple harmonic motion uses that same sinusoidal mathematics. This does not mean every oscillator contains a hidden wheel, and it does not mean every repeating motion is simple harmonic. Now compare two equal amplitude oscillations with the same omega. Give the second one phi equals pi over 2. It begins 1/4 cycle farther ahead. Its graph shifts left by 1/4 of the time period, while its height and repeat rate stay unchanged. Before adding any new dimension, hold the complete two-dimensional story. Radians measure progress around the circle. Projection turns that progress into sine and cosine. Uniform angular frequency turns angle into time. Amplitude sets the reach, and phase sets the starting place. There is a compact way to see both graphs at once. Let accumulated angle extend into depth while the point continues circling. The path becomes a helix, a circle carried forward as theta increases. Project that helix onto the horizontal coordinate plane, and its shadow is a cosine graph. Project it onto the vertical coordinate plane, and its shadow is a sine graph. The two familiar curves are perpendicular views of the same angle-indexed construction. The helix is a visual synthesis, not the path of the slider and not a claim that a physical wave travels in a corkscrew. Its depth coordinate represents angle or time. The actual slider still moves on one straight line. Many physical waves can be pictured as neighboring oscillators whose cycle positions vary from place to place. Their relative phase tells whether crests arrive together, arrive apart, or lie somewhere between. Phase is therefore essential when waves reinforce or cancel. Much later, phase relationships will also matter in the mathematics of quantum states and interference. We are not saying that a quantum state is a crank, a spring, or a classical wave. We are carrying forward the precise language of amplitude, frequency, and phase. Return to the opening recorder. Its horizontal axis is no longer blank. Every point on the curve now answers a physical question. At this angle, or at this time, where is the slider? Radians built the input ruler, and the rotating projection wrote the function. The height comes from amplitude. The pace comes from angular frequency. The starting place comes from phase, and the period and frequency tell us how the cycle fits into time. These are not separate vocabulary words, they are controls on one motion. Next, we will let two waves meet. Their phases can make them reinforce, cancel, or produce something in between. That question will lead us to trigonometric identities, superposition, and the mathematics of interference.